So let's get started. Starting with this one here. Predict the mechanism for each of the following reaction transformations. Want to predict the reaction here, the mechanism. Now, the first thing that you should be able to understand is what kind of mechanism do we have at this point. So you can see we are converting an alkene, right? This is an alkene. We are converting it to an alkyl halide. The reactant we are using is HBr. Now, one thing that you need to know about HBr, when you are reacting an alkene with HBr, you need to know that this reaction follows Markov-Nikov's addition. Okay? Markov-Nikov's addition. That is very, very important. And every time you're adding HBr, what we mean by Markov-Nikov's addition is you are going to look at your double bond. Let's say the double bond is like this. You have got this carbon here. You also have this carbon here. So if you look at, let me label this one as A, and then I label the other one as B. If you look at A has got three bonds. Which ones are those? The first one is this one. The other two are present in the double bond. So together there are three bonds at A, meaning that we only have one hydrogen attached at A. If you look at B, you have got two bonds from the double bond, meaning that you have got two hydrogens. Why am I saying so? Because each carbon is supposed to have four bonds. So when you're using Markov-Nikov's rule, where you have got a lot of hydrogens, looking at HBr, the H from the HBr is going to attach at the carbon with a lot of hydrogens. And then the B is going to attach at the carbon with a lot of other groups, not hydrogen. In other words, to attach at a carbon that has got fewer hydrogen. So that will be the mechanism that we are going to use. So I'm going to be writing them in steps. So step one, and it is better if you are answering such even in the exam to write it in steps like this. It's much clearer for to be followed rather than just writing it straight like that. So the first thing that is going to happen is that we need to know that the double bond acts as a nucleophile. So as a nucleophile, what that happens is that the double bond is able to grab the hydrogen from the bromine. That will make this bromine to be able to break off. So the double bond, this bond, the two electrons in the bond will go to the bromine. Now, as we have said, this reaction follows Markov-Nikov's rule. So what happens is that, now let me ask, if this is a carbon, let me label it A, and then this carbon at the end here, let me label it B. This hydrogen that we have grabbed from the HBr, where do you think it is going to attach? Is it going to attach at A or at B? Okay, thank you very much. That's the thing. So it will attach at B because it's following Markov-Nikov's rule. So what is going to happen is that you are going to have this, your hydrogen is going to be able to attach at this end. Now, when you attach at this end, the bond that you add is going to break off. So when the bond breaks off, this other carbon here is going to remain with fewer bonds. So when a carbon has got fewer bonds, it is going to be positively charged, just like any other atom, right? When that happens, remember in this reaction we had also released the Br. Now this Br is going to have two lone pairs which has come from the bond, but then Br still also has got three other lone pairs that we just didn't show here. Okay, it has got three other lone pairs. So because of that, it is going to have a negative charge. You can actually calculate a formal charge. Formal charge is given by group number. This one is a halogen, is in group 7 minus electrons in the outer shell. So if you count them in mass, these are 8. So this is going to give us a negative 1. So that is what we have there. The next thing that is going to now happen is that before this Br can come in, look at what we have. We have got what kind of carbocation is this one? Now, mostly when you are writing, we'll not even show this hydrogen, but it's there. Okay. What kind of carbocation do we have here? So what I mean, this carbon here is bonded to three carbons, one this side, two this side, Thank you very much. So it is a tertiary carbocation because it's bonded to three different things. Now, even if it is a tertiary carbocation, in this mechanism, what can happen is that you can actually form, okay, so you can actually form a tertiary carbocation within a ring. Now, what you need to understand is this. If you have got a tertiary carbocation here and a tertiary carbocation in a ring, let's say I've got a ring like so, it is more stable. The carbocation is going to be much stable when it is in a ring than when it is just like that. So what is going to happen is that in this mechanism, now let me write that as step 2. So I'm going to get the product at the end there with a positive charge. So this one methyl that you can, so this methyl, I hope you can be able to see that. So you have got a carbon here, this carbon which has bonded at this end. So what it can do is that it can break off from the position where it is bonded. It will go and attach where there is that positive charge. So let me count the carbons from the positive charge. So this is 1, and then this is carbon number 2, this is carbon number 3, this is carbon number 4. So you can see now we're going to form a ring that has got 4 carbons, because the fourth carbon is now going to attach at carbon number 1. So we're going to form a ring like this one, 4 carbons. But remember, let's say this is carbon number 1. Let me count them: 1, 2, 3, and 4. At carbon number 1, look, we have got 2 groups here, right? These 2 groups. So we are going to include these 2 groups here. But remember, we had removed the bond from carbon number 2. So after removing that bond from carbon number 2 is going to remain positively charged. Okay, so we're going to have a positive charge at carbon number 2 here. Now, what we have formed is a secondary carbocation, and the secondary carbocation is not very much stable. We're actually coming from tertiary carbocation, which is more stable. So we cannot move from a tertiary carbocation to a secondary carbocation. Why should we move from something that is stable to something that is less stable? So what will happen is that you are going to have another methanide shift or another methyl shift. This other methyl here is going to shift to where there is a positive charge at this point. And then what you'll be able to see is that you have remained with only one methyl here, also one methyl here. But the positive charge was at this point. When we remove a methyl from that carbon, the same carbon where we've removed a methyl is going to remain positively charged. So that is where the positive charge goes. And then now in step 3, we can see now we have formed again a tertiary carbocation. And the tertiary carbocation in a ring is very much stable. So the next thing that happens then, we are going to have this tertiary carbocation being attacked now by the bromine that we had released at this step. So I'll just show one lone pair of electrons. So this is going to come and attack there. And then what we are going to be able to see as our product is going to be this one. So this is going to be the product. That will be the mechanism for the synthesis of this one. Are we okay? Is the mechanism okay? Okay. Please, at any point, if you miss it, don't feel shy to get to just open your mic and speak. Okay, so that is the mechanism. Every time you see BR. Now take note, when you see BR alone, that will be the mechanism. It obeys Markov-Nikov's rule. But if you see BR with a peroxide, okay, like hydrogen peroxide or any other peroxide, it will go by Ant-Markov-Nikov's rule, meaning that if you have got a carbon that is more substituted, this carbon here, this is where your hydrogen is going to attach. And then the carbon which is less substituted, or the carbon with a lot of hydrogens, that is where your BR is going to attach. So that is the difference when you are using the same HBr, but you have got a peroxide. Very important. And you see the mechanism, I think, one of the questions. Okay, the next one. We want to provide a mechanism for the synthesis of the bromoalcohol that we can be able to see here from an alkene. Now, if you can see, we have reacted it with Br2 and water. So what is going to happen is in the first step, step 1, we are going to have our compound with a double bond. Let me write it like this. I can put the double bond here. And then the first thing first, we are going to have Br. Okay, we have got Br. Now I'm going to write Br like this, Br2. So the double bond is going to act as a nucleophile, going to attack this bromine. And then when it does attack that bromine, this bond is going to break off. But then this bromine has got lone pairs of electrons. So what will happen is that it will also act by attacking back. Okay. So that will be in the first step. So at the end, now what are we going to be able to see? We are going to see this double bond is going to break. So this is what we are going to have. And then bromine is having a bond that it is forming after being attacked by the double bond. But remember, it was also attacking the double bond, so it will also form a bond. So like you're having two bonds like that. So this bromine is going to have a charge, and that is going to be a positive charge at that point because it has got too many electrons. Okay. Now after then, the next thing that is going to happen, you are going to let me write that as a step 2, or I can write it just okay. Let me include it as step 2. So in the next step, the same product that we have. Now, before I go to step 2, is the formation of this compound okay? Is it okay? Yes, please. It is also nucleophilic. It has got those lone pairs of electrons. Okay. Now, in the next step, remember in the reaction we also have water at that point. So the water is now going to come in. I'm going to write it in this way as OH2. Now, water is going to be able to attack the carbon that is more substituted. So this reaction also obeys Markov-Nikol's rule. See, if you didn't have water here, remember at step 1, we also produced a bromine, okay, like that with a negative. So if we didn't have water, this same bromine would have come at this step and attacked this carbon. Now it can either attack from the front or from the behind. So meaning that the product is going to be two enantiomers. Now, in this mechanism, we also have water. Water acts as a stronger nucleophile than the bromine. So what happens is that instead of the bromine that was produced on the first step, water will be the one to be able to attack. So water comes and attacks at this point. When this happens, this bond is going to break off like that. So what will be the product? So we now have this a Br here, and then sorry, the Br is not going to be like that. Look at this, we had this carbon. So this is the carbon here. That is where we are going to have the Br being bonded at the end because we have broken just this bond at this point. And then we have also attached the water. Now we know water has got two hydrogens like that. Every time oxygen has got three bonds, is going to have a positive charge there. The next thing that is going to happen is that another base is going to come in, like another water molecule can come in at this point. So what happens is that this can grab that hydrogen, breaking off this bond. And then we are going to have our Br there, and then we have formed our alcohol. So that will be the production of this alcohol as a mechanism. Does it make sense? Yes, please. Okay. All right. So what we are saying is this: if you have got a double bond, let me write a simple double bond. Like you have got a double bond like this. Let me put just another atom here for the sake of orientation. And then we have got we are reacting this with bromine. What happens is that this double bond will be able to attack the bromine like this. When it does attack, this Br is going to leave. But this Br which is remaining has got lone pairs of electrons. So using one of those lone pairs of electrons, it will also go and attack like that. So it is being attacked and then it is also attacking. So what you are going to see is a bond like so. It is connected here and it is also connected here like that. It is going to be positively charged. Is this okay? Hmm. Okay. Okay. So the next. Mhm. Okay. All right. So is that another hand? Yes, please. Yes. Hmm. Okay. So every time you see X2 together with water reacting, you are always going to form a compound that has got X and also an alcohol. This X is representing halogens like chlorine, like bromine. So every time you see such a reaction with such reactants, you always have a product that is going to have an alkyl functional group and that same halogen. Hope does it make sense though? All right. So in the first step, the double bond is going to go and attack the bromine. That breaks off the other bromine. And then the bromine that remains will also be able to go and attack the double bond. So what we had, the compound that we had initially was this one. It had a double bond. Now the double bond has broken. Maybe it would have been more clear if I wrote this bromine down so that we see how the double bond is moving. So let me put a double bond like this. And then I write the Br like this. So what is happening is that the double bond is attacking the bromine, breaking off this other bromine, and then this bromine is also attacking like that. So what you are going to be able to see is that the bromine attaches like this. Now, if you notice, bromine has got two bonds here. It had three lone pairs, so it has got now only two lone pairs like that. Formal charge is given by group number. Bromine is in group 7 minus electrons in the outermost shell. Two lone pairs on top, two lone pairs down, that is 4. And then in this bond, you have got 1, that is 5. In this bond, you have got 1, that is 6. So those bond, in each bond, you only get 1 electron. That is the one coming from the bromine. So I've got 7 minus 6. That is the one which will give us a positive charge there. So that will be the first thing that happens. And then the next thing that happens, the same product that we have formed at this level is the one which now the water is going to be able to attack. So now we have got water. Now water always attack the more substituted carbon where the bromine is attached. So the more substituted is this one. That's the one which has got a lot of bonds. And then that will make this bond to break off. And then we are going to form our product here where we have our water which has attached. Now water has got two hydrogen and then it has formed another bond, so it is going to have a positive charge. And then this bond, look at how it is. It's like this. It has got 110 before you can have the bromine, so it's going to have 110 before you can have the bromide there. And then at this point, another water molecule always come in to be able to remove one proton there, and that bond breaks off. And so the product that we end up having is going to be just OH, and then we have got also Br there. We have also produced H3O plus, because when this water grabbed the hydrogen, we had now three hydrogens. Is this okay now? Does it make sense? All right, thank you. Let's go to the next. The next question here. Provide a synthetic plan on how the following transformations can be carried out in good yields. More than one step is required. Show all steps clearly, including the intermediates. No reaction mechanism is required. Now, here no reaction mechanism is required. For the sake of perhaps the question comes in a different way. So I'm going to also show the mechanism. But if you are answering this one, you just write the specific points which I will show without a mechanism. But in case it comes with a mechanism, look at, we are starting with this compound, and then we want to end up with this compound. So what did we have initially? We had Br. So we basically okay, so we have got a compound that has got two bromines. You can see both bromines have been substituted, and we only have a hydrogen there, meaning that the hydrogen had to replace the bromine. And then at this other point, we have got hydroxide. It means that hydroxide has to replace the bromine. There is already a hydrogen here, so this is the hydrogen we can see. And then there is already a methyl here. That's a methyl that we can see on top there. So there are a number of ways in which you can prepare the product, and that will depend with what comes to your mind when the mechanism has been given anyway. So let's start with the first one. Step one. Now look at what we have here. What we have is, let me write this. I'm going to write it like this, and then I'm going to write a methyl here, a bromine here, and then another bromine down here. Okay. Now, the mechanism that I'm going to use what is known as Vismo, sorry, Vismo dihydride, halide actually, Vismo dihalide. So this is what we are going to use. Now, when we are using this mechanism, what we are basically using is you are using zinc. Okay, we are going to be able to use zinc. So what is going to happen then when we are using this zinc? Let me, sorry. So in the first step, before I even write what is here, let me write the first step on top here as a step one. This is going to be another step. I'll write this as another step. So what is going to happen is we are going to have zinc. Now this zinc, when it breaks down, we are going to form zinc 2 plus and 2 electrons. Okay, that is what we are going to have. We have just broken down the zinc, and then we have formed zinc 2 plus and 2 electrons. So in this mechanism, the first thing that we want to be able to do is we are going to be able to use that zinc that we have formed. So let me write first the general mechanism, and then we see how it happens. So in the first step, what we do is we are going to be able to use zinc, and at the end of the process, we are going to form. So what is important for us to understand is, what does this mechanism, why are we using zinc? That should be the question that each one of us should ask ourselves. And then in the next step, what we are going to have is, we are going to have the first reactant we are going to use is BH3 in tetrahydrofuran. And then the second reactant we can use is water and the hydroxide. But then the question, okay, and then what are we going to be able to form from here? We are going to form the products which have been given. Now, if I just write like this, it doesn't make any sense. Why are we even saying that is how it is going to be able to happen? So that is what we want to understand. So for this one, they just said write the right, provide the what? The synthesis plan and also the intermediate. So you can just write this. But as a mechanism for understanding sake, when you are using zinc, what zinc does is that it makes an alkene. And how does it make an alkene? It removes the two halogens. So if you have got two halogens on a compound, zinc removes those two halogens and then it makes an alkene. That is what is important to understand. Okay, let's see how it's going to be carried out. So first thing first, as we said, that is step one. You can see which I've written on top there, right? Step one. And then in step two, we are going to have this compound Br, and then it has got a methyl, and then we have got a Br. So what is going to happen is that we are going to get one of the electrons that we have formed from the zinc. Let's say we get this electron. So we are going to come at this one carbon and be able to attach that electron. Okay. So we're going to bring this electron and come and attach it at this end. In this process, what are we going to be able to form? Now, if you notice, when we take that electron at that point, what happens is that the bromine is going to break off. What is the reason? Why should the bromine break off? Look at this carbon here. This carbon has got a methyl. This carbon has got a bromine. How many bonds are here already at this carbon? There are four, meaning how many electrons do we have for this same carbon which has bonded these four atoms? Yes. And that is what is very important to understand, because a carbon can't accommodate more than 80 electrons. Okay. The hybridization max it can have is sp2. I mean sp3. So it can't accommodate 9 electrons. So that electron that we have introduced will make this bond to be able to break off, and see what we are going to result with at that end. So we're going to have just a methyl there. And then remember, I've got a Br at this point. Now remember, what we have introduced is one electron. So that one electron will show it here. When you have got a compound, let's say I write X with only one electron, when we are writing odd number of electrons, we call those as radicals. Radical is a compound with the odd number of electrons. Okay, so that is the first thing. In the next step, what is going to happen? In the next step, the other electron, remember we had two electrons at this point, the other electron is going to come in. Now this other electron, when it does come in, is going to attach again at the same point where we had where we had put the other electron. So we're going to put it here. Okay, so what we are going to have is this with two electrons at this point, and then we have got our Br here. So before I do anything further, does this make sense? Okay. So what we just need to know is that about the mechanism with zinc, that is the visible dihalide. What you do is that you are going to be able to remove electrons from zinc. When you do that, you are going to have zinc ion. This is a metal. Those two electrons are going to be attaching at the position where you have got an halogen. One electron will first attach, and that will break off the halogen. The other electron will also come and attach at the same position. That is what happens. Is it okay now? Okay. So I'm going to remove what I've written on top there so that we can have space to write down. Let me also remove this. Okay, so the next thing that is going to happen now, we are going to get our, let me write that as as a step step 3. Since we wrote step 2, this one now comes in at this point with a Br here, and then it has got two electrons that we attached here, and these two electrons are as a radical. Now we are going to remove these two electrons from this point as a radical. When we do that, we are going to get these two electrons and come and form a bond here. I need us to understand here. So let me rub and write it again. I even write in a different color. So those two electrons which you have put here are going to move and come and form a bond. Pardon? Is that a question? Please, can you just say that again? Okay. Let me write them somewhere here so that it will be clear. What I'm saying is that we are getting those two electrons and bringing them here. Now we are bringing them to the direction that has got the other bromide. Because if I bring those two electrons at that position, what will happen is that this bromine is going to be able to break off. And then what we are going to be able to see is we have got a double bond formed. And then we have got a methyl here. The reason as to why the other bromine had to break off was because we can't accommodate more than four bonds. If the bromine was still here, we would have more than four bonds. Okay, because even if you can see, there is actually a hydrogen here. So there is a hydrogen here. So we're going to have a hydrogen, a bromine, and then this group, and then two bonds here, five bonds, and that is not possible for carbon. So that is why the bromine has been broken off. I hope this is okay. Does it make sense? Okay, thank you very much. Now, the next thing that we are going to use, remember we said we are going to use BH3, that will be in the next step. Now, what BH3 does is that we didn't only say we are going to use BH3. If you saw, we wrote on top, we wrote 1 and 2. So 1, we said we are going to use BH3 and the tetrahydrofuran. And then 2, we said we are going to use basically water with an hydroxide. So every time you see a mechanism, every time you see an alkene with BH3, BH3 basically provides us with electron, I mean with a proton. Okay, that is the main thing. BH3 will provide us with a proton as an hydride. What we mean by hydride is hydrogen with two electrons. Every time hydrogen has got two electrons, it's going to have a negative charge. The normal hydrogen that we know is H positive. This one is not an hydride, it's a proton. If you see H with a negative, that is an hydride. Where can we get hydrides? From BH3, we can also get it from sodium borohydride. You can also get it from FADH2. You can also get it from NAD. So every time you see, especially this one and this other one here, because these are the ones which are organic, these ones are less in Balchem. Just know that those sub compounds are just there to give you an hydride. And what an hydride does is because it has got two lone pairs of I mean, it has got a lone pair of electrons, it acts as a nucleophile. Okay, so that is what the hydride is going to do. It will act as a nucleophile. So this nucleophile is going to come in and attack at this end. And when you attack at this end, what happens is that the double bond which was there is also going to break off. So what is going to happen is that you would have attached, you remember uh, you have got a methyl here, this methyl. Now, if this methyl is in front, or let's say if the methyl is at the back like this, the hydride is always going to come at the front. That is because this reaction is happening like you can't attack from the front where you already have a group. So if this group is at the back, this hydrogen which is coming in can't attack also at the back. If this methyl which was present was in the front, the hydrogen always go at the back. So there's always that change. Okay, there's always that change. And then the next thing that will happen is that this carbon will remain with a positive charge. Now this carbon, even if you can't see, it has got one hydrogen. This carbon has got one hydrogen. You can just count the bonds. You already have got three bonds here, and then this bond. I mean two bonds there, and then with this bond. So those makes three bonds. Where is the other bond? We can't see it. That means that it is a hydrogen. The next thing that happens then is your second reactant comes in. You can use hydroxide, which is a stronger nucleophile. The hydroxide is going to be able to come in. The hydroxide is going to come and attack. Yes, please. So when a nucleophile is attacking a double bond, every time a nucleophile attacks a double bond, the double bond always breaks, and then you are going to have the attachment of the nucleophile. At the point where the nucleophile has not attached, there will always be a positive charge. I- Is this okay? Okay. So that is what is going to happen. Now, when this reaction is known as a sign reaction, that is, if the hydrogen attached in the front, the hydroxide that is coming in is also going to attach in the front. So look at this. Here you add the methyl at the back, you add the hydrogen in front. So the hydroxide that is coming is also going to attach in front, meaning that this hydrogen that is here is definitely going to be at the back. So that is the mechanism for the synthesis of this compound. But anyway, the mechanism was not needed. Now, even if you wanted to write like just the synthesis plan. If you do not know this, it will be very hard for you to propose. So, what should you know for you to be able to answer this question? What you need to know is that I first need to remove both bromides because I can't see them in my other product which is being given here. And the only way I can remove both bromides at the same time is for me to use the Visimo uh, dihalides. So I get to use a zinc to remove those two. And then when I've got a double bond, we need to know that when I've got a double bond, I can form an alcohol by using BH3 with water. So this tetrahydrofuran we can see is basically solution, so there is not affecting really anything here. Okay, just like a reaction is supposed to happen in water. And then also for the second reactant, that water you can see is just the solution where the hydroxide is going to be found for this mechanism to be able to work out. So that is what happens for this mechanism. Please, I know it can be a bit of trick. I'm going to upload the video, it's going to be open. If you don't get it well, go through it again and understand why we didn't choose anything else, but we chose this method. That is because of the two bromides. If we only had one bromine, it would have been very easy. We could have even used the SN2 mechanism, attacking, and then it leaves like that. So your choice of what you are going to use depends with the kind of reactant that you've been given. That is why you need to know the reactions, different reactions which alcohols have to undergo, and we've talked about all of those reactions, and the tutorials are there. Okay, let's look at this one, part 2. So what we have is this. We have got an alcohol. Look at what we are synthesizing. We are removing the alcohol. Now this should be very tricky. Look, if I remove the hydrogen, I mean the hydroxide, I'm supposed to form a compound like something like this with a positive charge here. Even if I was to move this bond here by a methyl shift, now every time you have got a reaction happening by SN1, you need to know that when you form a compound that is not stable, you are mostly going to have a shift. But there are some specific reactions that avoids rearrangements that we need to know. Reactions like oxymercuration, dematuration. Now the first thing that happens here is we need to remove the hydroxide because you can see in this product we don't have the hydroxide. But the question is, how do I remove the hydroxide? Hydroxide alone is a very bad leaving group because it is negatively charged. So what will happen is that I can use an acid here. I can use a protonated water, or I can use sulfuric acid like this. So what will happen is that this oxygen will be able to grab this proton, and then this bond will be able to break off. When that happens, what are we going to have? We are going to have this. We have got now our oxygen with two hydrogens. and this is going to be positively charged. This compound is a good leaving group, so this can now leave. And then what we are going to be able to have is this structure with a positive charge at this point. But then you can see in this reaction we are bringing in a bromine. Even if we brought in a bromine to come and attach at this point, we'll not be able to form this structure. It will be something else. You can actually you can try to do that. You see what is going to form. So if I brought a bromine to attach at that point, what you'll be able to see is going to be a structure like this. And that's not a structure that you've been given, meaning that that's not a possible synthesis plan. Okay. So then what do we do in that case? What we are going to be able to do is the first thing, the only way I can change this, the first thing that look, look at what we have. This is a secondary carbocation. Every time you have got a secondary carbocation and then it is next to a carbon that has got a lot of groups, just know that there is a possibility of a shift. So it's going to be a methyl shift. This methyl is going to move at this point. What you are going to have is two carbons are going to remain here, and then two carbons are going to be here. Now at this point, because I removed the methyl, I'm going to have a positive charge. Let me pause here a bit. Are we good? The first thing that happens is that your hydroxide, the oxygen grabs a proton. The reason we're doing that is to make the leaving group a good leaving group, and then the leaving group leaves. When the leaving group leaves where it left, you are going to have a positive charge. Because the positive charge is next to a carbon that is bonded to a lot of groups, so there's a possibility of a methyl shift. There's going to be a shift of that methyl. So that's why one methyl was shifted, it goes to the other carbon which had the positive charge. At the same carbon which where you add the methyl, that is where the positive charge is going to go after a shift. Good? Okay. Now, in the next reaction, what should we do then? At this point again, even if I wanted to bring in the next reactant, because what we want to use here is we just want to attach a bromine, right? We want to attach a bromine. Remember earlier we said if you use this HBr, when you're using HBr, when you see a double bond, okay, when you're using HBr, H can bond by the Markov-Nichols rule. H will bond where there's a lot of hydrogen, and then B will attach where there is fewer hydrogens. If you remember the first reaction we talked about. And this one can only happen when you're talking about what? Double bonds. And that's the only way I can get to attach in a bromine. Of course, there are different other ways, but that's a good way we can take for this one. But then I can only attach this when we have got a double bond. I don't have a double bond. So the next thing I should be able to think about is, okay, I need to have a double bond. Now the question is, where should I form my double bond? Because if I've got a positive charge here, the possibility is that I can have a double bond here. I can also have a double bond at this carbon at the end, or a double bond at this carbon at the end. What will determine where I need to put a double bond is where they've put a bromine. The bromine you can see is at the end, so I shouldn't put a double bond at this point. Because immediately I put the double bond at that point, it means the only possible points I can put my bromine is going to be at this carbon and at this other carbon. That is what you need to understand. When you're using HBr, you always attach the H and the Br at the point where you have got your what? Your double bond. So, how do I convert this carbocation into an alkene? Now, when you're converting, the formation of alkenes happens by elimination. We've talked about this mechanism also. Formation of alkenes happens by elimination. So what is going to happen is that, remember at this point, at this first step here, we have put a star. What did we form? We formed this compound, or SO3H. This was coming from sulfuric acid. We just grabbed one proton. So this remained with the lone pairs and the negative charge. So one proton that is at this carbon can actually be grabbed by this same guy. When we grab this proton, we are going to come and form a double bond here. And we are going to reform our sulfuric acid. So look at what we are going to have. We have a double bond here, and then we have got this. Haha, very good. So after we see this, okay, it is easy. I can now attach my what? My HBr. But wait, we said that the attachment of HBr, H is always supposed to attach where you have got a lot of hydrogens. B is supposed to attach where there is few hydrogens. Look at this. This point, let me label it as A, and then this point, let me label it as B. Which one has got a lot of hydrogens? So where do we think H is going to attach, and where's Br going to attach, at A or at B? Where? It will attach at. Thank you very much. So Br is supposed to attach at B, at this carbon. But wait, that's not a product that we have. But remember, when we were talking about the first reaction, what did we say? If we want the Br to be able to attach at the carbon that is less substituted, or the carbon that has got a lot of hydrogens, what did we say we should use together with HBr? Do we remember? Yes, we use yes, we're supposed to use peroxide. So that is going to be the thing that we are going to be able to use. Okay. So here, as I'm attaching my HBr, I'm also going to use peroxide. And that is, let me just write the word peroxide there, because we have got different peroxides that we can use, meaning that my Br will now attach at this end. So that will be the mechanism for this reaction. But then in this question, we just want a synthesis plan. So then, as a synthesis plan, what do you think we can write? The first step we can just have is our reactant. Let me have some space. Yes, please. Yes, you are just writing the reactants and some possible intermediates, the intermediates that you are forming. There's no need of a mechanism. Okay, no reaction mechanism required. So we are starting with this one. Just show what you did, what you reacted with. Here, the first reaction we reacted with sulfuric acid, right? With sulfuric acid, what did we produce at the end? We produced something that was first positively charged, and then we used the same sulfate which was produced at the end. So at the end of using sulfuric acid, we are supposed to produce what? An alkene. So at the end of using sulfuric acid, this is what you're supposed to produce as intermediate. And then the next reactant we are using is HBr in peroxide. And then now we write our final product, which is going to, let me write the Br there because there's no space the other side. So this is the synthesis plan with the intermediate there. Does this make sense? All right. Please be free to ask if you are not good at any point. Okay, let's look at this one. Complete the following reactions and give a detailed mechanism for the following. Look at what we have at the beginning. We have got a Br there. We are reacting this with ethoxide and potassium hydroxide with heat. And this is very interesting. If you followed our first class, when we're talking about SN1, how do you know what will be produced, whether it's going to be SN1, SN2, E1, or E2? So the first thing that you look at when you have got these reactants, when you have got ethoxide, ethoxide is a very good, this is a polar solvent. And then you have got a potassium hydroxide. Okay, the potassium doesn't affect the reaction here. Basically, what you have is a hydroxide, which is a good nucleophile or a strong nucleophile. So when you have got, look at the alcohol that you have. Let me just, sorry, not alcohol, but the alkyl bromide. Let me just mention this. When you have got a primary alkyl halide with a strong acid, sorry, a strong nucleophile. An example of a primary alkyl halide that I can write is something like this. This one is primary because the bromine is attached to a carbon that is only bonded to one carbon. When you have got a primary alkyl halide with a strong nucleophile, which is unhindered, and also you heat the solution, the reaction is more going to happen by SN2. Mostly when you're talking about strong strong nucleophiles are going to have O like R with a like this, the negative charge. For example, oxygen like this, okay, oxygen like that, whatsoever R that you can use, hydrogen or any group that you can use there, those are strong nucleophiles. If you have got a secondary alkyl halide, for example, like this, the same conditions, a strong nucleophile which is unhindered, and you heat the solution. This reaction is more going to happen by E2. If you use something that is tertiary, a tertiary alkyl halide, for example, something like this. Yes, please. The what? So when you have got a primary alkyl halide, strong nucleophile, which is unhindered, and you heat your, you are also having heat, you are heating your solution. Reaction goes by, mostly the major product will be formed by SN2. Now you are also going to have the reaction by E2. So this reaction is radio selective. And what we mean by that is that you are going to have major product and minor product. Major product is by SN2, minor by E2. When you use the same strong nucleophile, but it is also unhindered, and you are also heating, but then you have changed, you are using now what? You are using a secondary substrate. The reaction is going to have the major product by E2, and then the minor product is going to by SN2. You're also going to have a minor product. Now, if you change, you are now having a tertiary alkyl halide. The same reactants that we have here. Mostly it will depend on temperature, right? The mechanism is going to mostly happen by E2 or E1. If there is supposed to be any substitution to happen, it will just be SN1. You can't have SN2 for something that is tertiary. It is too hindered. So the video that we did on the previous one, please, if you follow it, you get to understand this very well. But then if you hit your reaction, you are not going to have any product by substitution. So you are only going to have one product, and the reaction is going to be radio specific. And what we mean is that you not have minor and major product, you only have one product. So now look at what we have. We have got a stronger nucleophile. We have got a strong nucleophile. We are heating, and the nucleophile is hydroxide, meaning that it is unhindered. And then the substrate is secondary. What mechanism do you think this is going to happen by? Okay, thank you very much. So it's going to be by E2. And every time you hear about elimination, elimination reactions always result in the formation of alkenes, a double bond. Substitution reactions are just replacing one compound with the other. So in step one, what we are going to have is, I'm going to write that. So let me write that as step one. We have got our ring. And then we have got this, we have got a BR there. So the nucleophile is going to come in. Now the nucleophile, the ethoxide, the ethanol is the solution. So the nucleophile is the hydroxide. Now this nucleophile, what it does is that it is going to grab, when you're performing the reaction by elimination, you grab a proton one carbon away from the carbon in the double bond. Look at this. Sorry, not the carbon in the double bond, but the carbon bonded to the halogen. The carbon bonded to the halogen is this one. So just move one carbon away on either side. So you have got a hydrogen at this carbon, also have a hydrogen at this carbon. So what can happen is that the hydroxide can come and grab this hydrogen. If it grabs this hydrogen, what you'll be able to do is that this bond will break and it will come and form a double bond here. When that double bond forms, this bromine will be able to leave. That is the E2. You can see there's an attack formation of double bond and bromine leaves at the same time. So that what we're going to have is this, a double bond here. But again, the same hydroxide could have also attacked the other hydrogen. So this hydroxide could have grabbed this hydrogen. This would have still led to the breakdown of this bond, and that would have still pushed away the bromine. So the other product we can have alternating bonds inside there. The double bond, look at what it has formed here. So the double bond has formed here. So these are the two possible products. But then the question is, which one is the major product? Can someone try that one? Which one is going to be the major product, A or B? Okay, thank you very much. So B is going to be the major product. And the reason for, okay, and the reason for that is we are grabbing a hydrogen that is a secondary. Here we are grabbing a primary hydrogen. All right. So that is what happens. So that will be the end of the first step there after we use the reactants on top. And then now we're going to use now the reaction down. That is going to be step 2. Now you can see we're using HBr with a peroxide. I think now we know what we are going to form. Okay. So I've got alternating double bonds. I'm going to write this with a double bond here. I'll also write the other one. Alternating double bonds with a double bond here. Now, the goodness for, okay, let me not write like this. I wanted to just go direct. Okay, before we even do this, let me use this one. Between A and B, where is the BR going to attach? Yes, when we use peroxide. Okay, so yes, that is correct. So it's because we are using peroxide, instead of the BR coming to attach to the more substituted carbon, it will attach at this carbon. Very important. But then for this one here, just take note. I only use one. I only use one compound. So let me just write the final products, and then I write a mechanism because it will take us time. I write a mechanism of only one, how we are going to form. It will be the same with the others, so you'll be able to finish up the others. So for this one, the final product you're going to form is that the BR is going to attach here instead of attaching here. The reason for that is we are using peroxide. If there was no peroxide, BR would have attached at a point which the doctor said at this carbon here. And then for this one, now if you can see this other compound, the the double bond is equally substituted on both sides, meaning that the BR can either come and attach here, or it can attach here. I should have written this one down, but then there is no space there. Okay, so these will be the three products. But then let's write the mechanism. How are you going to move from this one to this one? We know we are using HBr with a peroxide. How are you going to move? So when you are using HBr, just know that we convert uh, alkenes to alkanes with a bromine. Or let's say if it was something else, it was like HX. We are going to convert the alkene to the alkane with the X. The X is the halogen. Okay, let's write the mechanism now. Hope this is okay. Is it? Is this okay? It's quiet. Hope I've not. Yes, please. Yes, please. Mm. You're writing the mechanism for the formation of the three products. Okay, so I'll only use this one, which is here. Remember, in step one, we formed this compound. This compound was formed in step one. And then I'll now use step 2 using the two reactants which are down there. Now the first thing that we are going to get is we are going to get our peroxide. How is peroxide? If it was hydrogen peroxide is like this. But then they've just said peroxide, this is going to be R2O2, whatsoever R group that is attached there. Okay, so this is like this: R bonded to oxygen, and then another oxygen, and then bonded to another R. If it was hydrogen peroxide, it's like this. So I'll use a general form for a peroxide because I've just said peroxide. Okay. The first thing that is going to happen is that this peroxide is going to break. The bond between the oxygen is going to break. Now oxygen, because oxygen is equally electronegative, so there is no oxygen that has got a capacity to pull the bond more than the other. So what happens that there will be homolytic cleavage. By homolytic cleavage, what we mean is one electron will go this side, the other electron will go this side. If you can see it, please take note of the arrow. It's a half arrow. Very important to understand. This is a half arrow, not a full arrow. Okay. So what is going to be produced at this step is going to be Ara bonded to oxygen. Now what you are going to be able to form is a radical. Why a radical? Because this oxygen has got one electron, and then the other oxygen is also having only one electron. Okay, so such compounds we call them radicals, but the breaking of this compound requires heat. You can't just break it like that, so we are going to use heat there. That will be the first thing. Now in the next step, remember we had peroxide and HBr, and that, let me write that as step 3. What is going to happen in step 3 is our HBr is now going to come in. So let me write first the R. I'm only using one of these compounds that we've gotten after breaking the peroxide, and then I'm going to write my HBr. But then at this step, what is going to happen is that this is very important. This a similar mechanism came in test 1. It was for, I mean, test 2, a radical reaction, a radical mechanism. Now for a radical mechanism, what happens is this is not, it's not the same as the attack that we know, because we only have one electron here. Okay, we only have one electron. What is going to happen is this one electron is going to go like this. Look at the way I've written it. And then this bond with the HBr is going to break. We are only getting one electron, only one electron. It will come this side. The other electron that remains is going to go with the Br. So the product that you are going to have is going to be R. Now remember, oxygen brought one electron. The hydrogen has also brought one electron. So you are going to have a bond now. So you have got RO and then a bond with the hydrogen that we have formed. And then Br also has become a radical. Why has it become a radical? Because it took one electron. So that is how we write radical reactions. Very important. This thing, similar, something similar came. But then they were talking about something like this, account and explain why it is more stable and such. Anyway, we're going to answer that in tutorial sheet number, that should be number 5. Okay. Are we okay at this point? Are we okay? Okay, it's really quiet. All right, so now we're going to have step 4. Now in the next step, we're going to get now the alkene that we had formed earlier. This is the one, like that. And then we are going to use the 1Br, which has got a dot there. What are we using? We are using a radical for bromine, a radical. So what happened is that this radical is going to come and react, is going to come and react with the double bond. Now, how does that happen? Remember, every time there's a reaction between a radical and another bond, it's different from the actual one that we use. So here, double bond will take an electron like that. The radical also take an electron like that. So these are now going to form a new bond. Okay, a new bond. Look at how this is going to go. We now have this. Now the question is, where is the, okay, please pardon me, I've not shown something here. When this happens, let me first remove this which I wrote here. I broke one bond, but I forgot the other one. So we are having this. There's a cleavage of this double bond. One electron goes like that. The other electron is the one which comes with the bromine. But the question is, where is the other how about the other electron? So you need to show the other electron. The other electron is going to go like this. Now, this is the main reason as to why you end up attaching Br at the end. So we are going to form Br at this point. There is going to be an electron that is going to be here. It will just be alone as a radical. If we did the opposite, let me say this is a phenyl. I'm representing this thing, this ring, and then it was like this. Say we had attached the Br here. It means that that other electron would have formed here. Now, we talk about the stability of the radical that we have formed. This is a secondary radical. This is a primary radical. A secondary radical is more stable than a primary radical. So that is why this mechanism ends up attaching Br at the end instead of attaching Br on the middle. We consider the formation of the radical. We want the more stable radical to be formed. That is the thing about this mechanism. Okay, that is going to be our product. Are we good here? Okay, thank you. Now we are going to have the next step. Let's write it as step 5. Allow me to write this as phenyl so that I reduce on writing very much. This ring, then we're having something like this. Now the next thing that is going to happen is that we don't want this to be a radical, so another HBr is going to come in. Okay, this radical again will go and do this, take its electron. This double bond takes one electron like that, and then this bond also breaks, taking one electron there. So what are we going to form? We're going to have this group, and then we have got this a Br here. Now we have attached a hydrogen here. But when we are forming hydrogen, like, we don't even show, right? So you can see the hydrogen attached at the carbon which was more substituted, the bromine and the carbon which is less substituted. That is what we call anti-Markov-Nichols, the substitution. And then you have formed also another Br radical. So that is going to be, just a moment, just a moment. Someone was calling. Are you able to see back now? Okay, let me just do it again. I bet it then. Have we understood step 4? Okay. So in step 5, what is happening is that this same product that we have formed here. Let me write it. With a Br at this end, it has got a radical here. It has got one electron there. Now we can't just form our compound with a radical like that. What is going to happen is that the same HBr that we had used at the beginning is going to come in, HBr. So this radical is going to, this electron will come like this, and then from the HBr we're going to get one electron with the hydrogen, and then the other electron is going to go with the bromine. That is how we are going to end up with our product. Let me write, this is representing the ring, the phenyl I've written there. So we're going to have a hydrogen now to have attached at this end, and then we have also formed Br with one electron because it is a radical. Is that okay? Yes. Okay, so that is the end of that mechanism. You can see how long it is, right? So let's go to C, part 2. So what should you take from this? If you see the reactants they've given you, you should be able to predict by what mechanism. The first thing, before talking about the mechanism, you should be able to know what is my product going to be. Am I going to go by Oxidation, is the reaction going to be nucleophilic? Is it going to be elimination? Is it going to be substitution? What will be the reaction? What will be the product? That is what you want to do when you see a question. Okay, let's look at 2. Now 2, we are reacting sulfuric acid with the this is ethanol. That's C2. Something that you need to take a note about this one, every time you have got an alkene, this is called acid catalyzed hydration. You are going to use an acid, you are going to use water. Just know that you always form an alcohol. Acid catalyzed hydration of alkenes forms the alcohols. But then we have just changed, we have not used an alcohol here, we have used instead oh, we have not used water, instead we have used an alcohol. So when you use an alcohol here instead of water, just know we are going to form an ether. Okay, that is what changes. It's important to take note of that. So what will be the mechanism? Step 1. In the first step, we are going to have our ring double bonded to oxygen. I mean, there's no double bond to anything. The first thing first is that your acid, the sulfuric acid, I like writing the sulfuric acid in this way. The first hydrogen at the beginning, the last hydrogen at the end. And then one oxygen at the beginning, three oxygens at the end, and then a sulfur on the middle. So what will happen is that the double bond is going to be able to grab the hydrogen, and then this bond breaks. For every reaction that you talk about, you need to understand, is it going to go by Markov-Nikov's rule or by anti-Markov-Nikov's? So this one is going to be able to follow the Markov-Nikov's rule. We want to form the most stable carbocation. So what is going to happen is that when the double bond grabs that hydrogen, the hydrogen is going to attach at the carbon that has got a lot of hydrogens. So it is going to attach at this carbon, meaning that this other carbon is going to remain deficit of electrons, so it becomes positively charged. Is this okay? Okay, and then the next step, the carbocation that you have formed. Now the next thing that you look at is the carbocation that are formed stable? This one is a tertiary carbocation and it is in a ring, so meaning it is very stable. So the next thing that happens is now you use your methanol. Actually, ethanol, not methanol. So I can also write this as oxygen bonded to an hydrogen, and then we have got two carbons. I can just write the two carbons like this. Now this oxygen has got two lone pairs of electrons. Was that a question? Okay. So the oxygen will come and attack where the double bond is. Now this should tell you that your final product can either be you are going to have a racemic mixture. What we mean by that is that this OH which is going to attack can either attack from the front or from the back. Every time you have got a reaction happening by SN1, you first had the formation of a carbocation. The thing that is coming to attack, the nucleophile coming to attack, can either attack from the front or from the behind. So if they wanted us to show stereochemistry, we are going to have two possible structures. So one possible structure I can write is I can write the hydrogen on a dash, and then the group that is coming, I can write it on a wedge, or I can write the hydrogen on the wedge, the group which is coming in, I write it on the dash. So we are going to have a mixture of enantiomers, and we call that as a racemic mixture because they are going to be in equal concentration. So this is going to be a methyl. You have got oxygen here, two carbons, a hydrogen. So this compound, this is going to be positive charge because the oxygen has got three bonds. And then the next step, that is going to be step 3. The product I have formed here will just remove now the proton so that it becomes uh, neutral. So I've got oxygen like that. So we can use another. Now in solution we have got a lot of water here. Even if of course we can't see that there's water, but in solution I've got a lot of water. But for that sake, let me just use what was produced at the first step. What was produced at this step was this, with a negative charge. So this can come acting as a nucleophile, grabbing that hydrogen, breaking off this bond, and then we would have formed our ether. So this is going to be the product and ether. We are good? Is there a question anywhere? Are we okay? So the next reaction. We had talked about this reaction before. The only difference that we had used Br2 with water, but here we are using with the sodium chloride. So the first thing first, for this mechanism, every time you see Br2, don't forget what we are doing. The Br is like that. What is going to happen is that the double bond is Z attacking the Br, breaking off this bond, and then this is also attacking. So what is going to be formed? We are going to have Br attaching at both ends. It's going to be positively charged. This is step one. Is this okay? Okay. Now for this one, they've said write all possible products. Now the next step, step two, will depend with what you are going to use. So the same product that we have formed here, look at what we have. This one. So what is going to happen, just like the previous one what that we talked about, we are going to have your nucleophile. The nucleophile always come and attack the carbon that is more substituted, right? That's what we said. And then this bond will break off. So the product that you are going to have is going to look like this. You are going to have your Br here, and then the nucleophile will come and attach here. What have we done? We have just broken out this bond, and then this is the attachment of the Br. Now for this mechanism, you need to understand, I forgot to mention it for the first one that we talked about. The products always face on opposite directions. So we'll not write this nucleophile here. Instead, this nucleophile will be written here. And then this methyl is the one that I'm going to write here. You can see they're on opposite sides. Just take note of that. But then I've just said nucleophile. So what are the nucleophiles that we have? Even if you can't see, every reaction happens in water. We can't just have Br2 reacting in sodium chloride. Sodium chloride is a salt. So if you don't dissolve it, then how is it going to react? It can't react. So meaning that one possible nucleophile you have is water. The other possible nucleophile that you have, yes, yes, it is dissolved. So that means just the aqueous there means that we have got water in solution. So one possible nucleophile we can have is water. The other possible nucleophile we can have is, remember we had released the one Br on step one, right? That one Br which was released can also come as a nucleophile. And then the other nucleophile that we are going to have from the sodium chloride, sodium doesn't affect the reaction, meaning that we have got a Cl as another possible nucleophile. So if it was the CO attacking, what are we going to be able to see? This is the structure Br. The only thing is that where there is nucleophile, we are going to attach Cl. If it was Br, this is going to be the product. We are going to just put Br here. If it was water, now for water it is going to go into two steps. Okay, we'll say it again. So your Br is here. So if it is water, then water will come and attach here. But remember, water has got two protons. So this is positively charged, but you're supposed to form an alcohol. So what will happen is that you are going to use another water molecule to be able to remove one proton from here, and then the bond breaks. Let me just quickly do the step two again. So in step 2, what we are doing is we are getting what we have formed at the end of step 1. This is it. We have got Br there attached at these two ends. What are we going to use? We are going to use different nucleophiles. Now, in this one, we have got a lot of nucleophiles. Because of aqueous, meaning that water is one of the nucleophiles. A nucleophile is anything that has got lone pairs and can attack. Okay. A chlorine here, a chloride ion is also a nucleophile. Also, a bromine ion, which was produced at this stage, is also a nucleophile. Let me use water as a nucleophile. If we use water as a nucleophile, what is going to happen is that water is going to come and attack at this carbon. We are always attacking the carbon that is more substituted. When that happens, that will fully break off this bond. So what we are going to have is, I'm going to write this methyl on top like that. And then I'm going to write this group here like that. Let me write it in this way. If it does confuse, we're going to have a Br at the end. This is a Br here because we've broken the bond. And it is having this carbon, and this carbon, three carbons. One, two, three. The other one is where the other bond I'll put is where the OH is coming actually to attach, I mean. Now remember we have said that they are supposed to attach on opposite sides. So if the Br is down, OH is supposed to be on top here. But OH with two hydrogens is water. I mean it's positively charged. So use another water molecule to be able to grab a proton here. This bond breaks off. So what are we going to be able to see? Be able to see this. We have formed an alcohol with a Br. If we had used chlorine, which is an ion, it will basically just come and attack and break the bond. So there will be no need of going to another step. It will just be a direct step. So let me just write it on top there. So I've got three possible structures as products here. So if we use Cl minus, using a lone pair to go and attack this point, this bond breaks off. So look at what we are going to have. What I've written is just this carbon, and this carbon. And then here, this is where the Br is attached. And then we are going to have the attachment of a chlorine, but I'm not attached the chlorine on top there. Instead, I'll attach it down here. It's supposed to be opposite sides. That is what the other Br also do. The Br also come and attach here. So three possible structures. Is this okay? Okay. I hope no one is not speaking if they are not okay. Give the structures of the major products or the following reactions. Now, I've already talked about this mechanism. Look at this. You are adding HBr and then you have got a double bond. What are you going to form? We've already talked about it. We just want to write a structure. Yes. Okay, we're going to have this. Where are we going to attach the bromine? Is it at A or at B? Remember, I've got a peroxide there at B, yes. So we're going to attach. Is that a question? Please, if there's a hand, docs, you can go on. Okay, for the next one, you are using sulfuric acid and water, and we already described this mechanism. This is called acid catalyzed hydration of alcohols. I mean of alkenes. What do we form? What did we say we are going to form? We form an alcohol. But then, is the alcohol going to attach at A or at B? At A. Remember this one follows Markov-Nikolsky addition. And then now we are using potassium permanganate in water, but this is a cold solution. Now, when you're using potassium permanganate in water and the cold solution, you need to know your product is, you are going to basically add two alcohol functional groups, add a double bond. That's what you need to know in the cold solution. So we're going to attach now the alcohol function groups which you are going to attach they are all going to be on the same side. So you can write it like this, or you can write it like this. So your two alcohol functional groups always attach at the same end. But if you use the same solution, the potassium permanganate, but you are heating, this will become an ozonolysis reaction. Ozonolysis. So what will happen is that you are just breaking this bond on the middle here. All right. So look at what you are going to have. You have got this, and then you have, remember, you have broken also at the other end. So we have just cut on the middle. Simply attach an oxygen at this point. So this structure, let me first explain this when you're using ozonolysis. When you're using, sorry, this is not ozonolysis. It is oxidative cleavage. When you're using ozone, oxidative cleavage is called ozonolysis. But when you're using potassium manganate, it's just called oxidative cleavage. Ozone, ozonolysis, it's also oxidative cleavage. Now, if you see after we had broken the bond on the middle, what resulted? This one. This double bond has got how many groups? It has got one group here and another group here. Is this primary, secondary, or tertiary? When a carbon has got two groups, what is that called? It's a secondary carbon. So this carbon here, which has those two groups. So you need to know that when you're using potassium permanganate, and then you have got a you have got a secondary double bond. You are going to reserve. You are going to end up with a ketone. That one you need to know. Secondary will form a ketone, and then for primary, supposed to form a carboxylic acid. Okay, and then for one which is not unsubstituted, this one you are going to form carbon dioxide. If you look at this, you only have one carbon here. Remember, we had the carbon here, we had the carbon here, we had the carbon here, we had the carbon here. So I've broken on the middle, meaning that you only have one carbon. So if you only have one carbon, we call that as unsubstituted. So what do you think we are going to form from this one? What will be? Yes, it will be carbon dioxide. Okay, very important to understand that. So this is going to be double bond to oxygen, carbon, double bond to oxygen. But here for the other one is a ketone, so just attach an oxygen there. This would be different when you're using ozonolysis. When you're using ozonolysis, you are going to have uh, ozonolysis will depend with the next reactant that you are going to have. But this will produce like ketones, right? Sorry, aldehydes, but it will depend on the next reactant. I hope that there's an example in this question. Is this question okay? So when you are using ozonolysis, when you have got something that is secondary, you are using ozone, it will depend with the next reactant. Okay, let's say we are using methyl dimethyl sulfite. If it is secondary, you still form a ketone, it doesn't change. Another reactant that you can use as a second thing is hydrogen peroxide. It will not change anything, you still form a ketone. But when you're using something that is primary, ozonolysis, if you use methyl sulfate, you are going to end up with an aldehyde. But it's different when you use hydrogen peroxide as a second reactant, you are going to form a carboxylic acid. So that is what you need to know about ozonolysis. But for this one, you always form like that because it is a very strong oxidizing agent like that. Is that okay? Okay. B. Consider the following reactions and deduce the starting materials and draw the structure for each. Now, if you can look at the reactants, you have got potassium permanganate, hydroxide, and water and heat. Immediately you see potassium permanganate and heat, what should you think about? You are thinking of ox. Thank you very much. Oxidative cleavage. Okay. Now look at what you are cleaving. You are cleaving something with 8 carbons. So you want to write the structure of that compound with 8 carbons. So basically, what you do is just get this, get your two structures which you formed as your products. I'm also going to write this one such that the functional group will face this direction. So how many carbons are here? 1, 2, 3, 4, 5. So I write it like this, and there's OH at the end, double bond with oxygen here. So that is carbon 1, 2, 3, 4, 5. So if we count the carbons, this is 1, 2, 3. This is also 1, 2, 3, 4, 5. So the only way you can have a compound, you can see if you add 5 plus 3, that will give us 8, and that is the structure there, right? So meaning that the bond was broken between these two carbons, this carbon which is here and this carbon that is here. So if I start counting at one end, if I start counting from this end, 1, 2, this will be 3. If I start also for this other one, it is better if you start counting from the other end for the sake of you knowing where the double bond was broken. So this will be 1, 2, 3, 4, and 5. So this means that the double bond was broken between carbon number 3 of one of carbon number 3 and carbon number 5. Now what? I know that is a bit confusing. Okay. So this just means that we had something like this. Write 8 carbons: 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. But then what you need to understand is, from where did we produce this? Was our compound primary, secondary, or tertiary? Remember, we're using potassium permanganate. And look at what we are forming. We are forming a carboxylic acid. This is also a carboxylic acid. So let's speak. Where are we forming? Where are these groups monosubstituted, disubstituted, or unsubstituted? Thank you very much. They were monosubstituted, both of them. And remember, for monosubstituted, basically this one, how was it? It was like this. Okay? It was like this. So we just attached an oxygen on top there, and then we added OH at the end. Same with this group, it was like this. Okay? Like this. We just attached the oxygen on top there, and then we added OH this side. So what we'll do is that we are going to get this end and this end, we just attach them. So if I start counting from this one, 1, 2, 3. 1, 2, 3. So you see, we are going to have a double bond here, meaning that this is where the double bond was broken at carbon number 3. If you start counting from the other side, 1, 2, 3, 4, 5. Same way with this one. 1, 2, 3, 4, 5. It was at position number 5 where the double bond was broken. So this is the compound which was broken. That is how you can come up with it. So it's really easy to come up with the compound as long as you understand what monosubstituted, disubstituted, and unsuch substituted are going to be able to form. Okay, let's look at the next one here. Look at this one. Look at the functional group. Was this monosubstituted or disubstituted? How about this one? Okay, so meaning that these guys were like so. They were like so. Basically, there was a double bond here. We just attached the oxygen on top, and then we attach OH down here. And then the other one, no? Let me write it like this. It was like this, right? OH, like that. So I'm going to now write it like this. It means that this compound was actually like this. We just attached an oxygen on top and an OH down here. What I'll just get this one and come and attach it on top here. Very easy. Okay. What are you going to form? You have got this double bond here. I've come and attached this one also. So I've attached this one also, but remember it has got another carbon like that. So this is the structure. If you count how many carbons you have here, is 1, 2, 3, and then the ring has got 6, meaning we are now having 9 carbons. And then you can say from the formula that we also have 9 carbons. That is how we form this. Very easy like that. Is that okay? Okay. The next one here, question 3. Just remaining with a few questions. Give structures for R and S and write detailed. I love these questions. Detailed mechanism for the reaction. Now, for such a one, look at what we've been given. What is this compound? Do we know it? Yes, tosylate chloride. So the thing is this, if you don't know the structure for tosylate chloride, you can't answer this question. Now, a tosylate is basically sulfur dioxide. You can see from the name tosylate chloride, you have got a chloride, and then you have got a ring, which is six membered. It has alternating bonds inside. So opposite to where the sulfur is, you are going to have a methyl, just direct opposite. If you put this methyl somewhere else, trust me, then you are ready to lose marks. If you can't remember this structure, you are also not ready to get the questions. This thing came, I don't know if that was test 1 or test 2. Okay, so what should we remember about the tosylate? They'll give you this structure just like that. You also have methylates. Okay, you find it like that, or mesylate chloride. It's all the same sulfur dioxide with a chloride, but a mesylate chloride just put a methyl here, that just a methyl. What differentiates a mesylate chloride from a tosylate chloride is just this same group here, just that. So please, just make sure you know that structure. It's not hard to know. It's just sulfur dioxide. One end you have got a chlorine, one end you have got a benzene ring, but it should have an a methyl opposite to where the sulfur was attached. Okay, as a mechanism, the first step, step 1. Now the reason as to why we use tosylates, mesylates is just because they are better leaving groups than a hydroxide. That is the thing. Okay, we can also use things like which you can convert hydroxide to a water, which is a better leaving group. That is the aim of this mechanism. Basically converting the hydroxide into a good leaving group. So the first step is just converting the hydroxide to a good leaving group. So the final product R will be that. So look at this. You have got the hydrogen at the back and then the hydroxide in front. Now I'll not be showing the hydrogen at the back. You can be showing it as you write, but it means the same. If I show the hydroxide in front, definitely it means that the hydrogen is at the back. So the first thing first, what will happen is that we're going to have our tosylate chloride, sulfur bonded to oxygen, double bonded to another oxygen, a chlorine. Remember, we have got a ring down here. It has got alternating double bonds. What will happen is that the oxygen in the alcohol acts as a nucleophile, comes and attacks here. When that happens, one double bond with oxygen is going to be able to break. Okay, that is what you need to take note of. The product is going to be, we still have our group here. Oxygen is still here. Remember, it's still bonded to a hydrogen. And now it is going to be bonded to sulfur. This is bonded to a chlorine. This is bonded to oxygen. But this oxygen, it will now be a single bond, right? Because we have broken the double bond. And as a single bond, is going to have three lone pairs and it's going to have a negative charge. Don't forget that. And then you have got another double bond with oxygen. Don't forget it, which is this one here. And then we have got now this bigger group down. Is this okay? Does this make sense? Okay. The next thing that is going to happen is that the oxygen that has the same double bond that we had broken from the oxygen, one lone pair will still move back and reform the double bond. When that happens, the chlorine is going to be produced. So we are still going to write our compound like this. You can see I haven't changed any configuration. Still have a hydrogen here. Please don't forget, I've forgotten something important. This oxygen is positively charged because it has got three bonds. Okay. We're going to have the sulfur, but remember the chlorine has been, this chlorine has been removed, so we are not going to have that chlorine. But then we have got this oxygen at this end which has formed the double bond, so I'm going to write it on top. And then we also have this other oxygen here which has got a double bond. I'm going to write it this side. And then we have got the ring down here. Don't forget a methyl just opposite. So this is the structure that we are going to form. When we form this, now we can use our pyridine. Should also know the structure for pyridine. Pyridine is a six-membered ring. Uh, so the first thing that happened was the hydroxide attacked the sulfur. A double bond was broken. That double bond which was broken is going to reform. When that double bond reforms, the chlorine is going to be expelled. This chlorine is going to be expelled. So those are the first two steps that we have done, reaching here. So in the first one, we had to form this structure. What did we do? We just attached oxygen to the sulfur, broke the double bond. That's the only thing that happened. The same double bond that we had broken is going to be reformed. As it is reformed, this chlorine is going to be expelled. That is what happened in the next step to form this one which we are at. Okay, are we able to see now? I don't know if you got the explanation before the something disturbed here. Okay. So when we form this product at this point, immediately you form this product, the next thing that comes in is a pyridine. Pyridine is a six-membered ring. It has got five carbons, but it looks like a pyranose. Pyranose means six member. Yes? Oh, I've just forgotten it. It's still there. So pyridine is six-membered with a nitrogen at one end that it has got alternating double bonds. Please, it's alternating. So what happens that this nitrogen will go and grab this hydrogen here, and that will break this bond. That will be our product. And the product is still have oxygen here, bonded to a sulfur, double bond to oxygen, and then we have got a group down here, alternating double bonds. So this compound that we have formed here is the R. Okay, that is R. Eh, Immediately you use the pyridine. Now the next thing now we can use our cyanide. Now potassium and sodium, they're group 1 metals. They don't affect the reaction. Their aim is just to make sure that the ion that we have is neutral. Because cyanide is negative like this, sodium is positive. So I just want to maintain our cyanide neutral. That's why we are going to see it as sodium cyanide or potassium cyanide like that. So the next step that comes in is the cyanide comes in. Now cyanide acts by SN2 mechanism. Very important, very, very important to understand that it's SN2. So what will happen is that this is going to be attacking the same carbon. Okay. Yes, please. Okay, that chlorine is still there. What can happen is that, yeah, the chlorine is still there. And that chlorine, in other books, what you are going to see is that the chlorine that was released, remember the pyridine had to grab a proton, right? The chlorine can actually react with that proton which was grabbed to form hydrochloric acid. Pardon? Okay, for here it's specifically pyridine. Pyridine will always be the one to grab that hydrogen from this oxygen here. So cyanide is now coming in and it is going to attack where oxygen is bonded. Yes, please. Mm-hmm. Mm-hmm. Yeah, so that is what. Okay, thank you very much. That is what happens for most of these ions actually. Okay, just like sodium cyanide like this. In other books, you are going to see it will be written like this. Okay, to be written like this. It's all the same. So the chlorine is negative. It will just be, remember, negative things are attracted to positive things. So it just have that closeness with a positive charge. But that is not something that will affect your mechanism whatsoever, or it will make you to be penalized for anything. Okay. So the cyanide now is going to come in at the very positive. So look, we are hydroxide. What would have happened is that this hydroxide would have just left like that. Okay, just on the first step, what we would have done is we would have basically used our cyanide. Cyanide would have been used. It comes just direct, attacks here, and then releases hydroxide. But because hydroxide is a bad living group, that's why we had to convert it to a good living group, which we've written here. So the cyanide is going to attack, and then the whole of this bond is going to break. The oxygen is also going, just like the hydroxide would have carried the oxygen. Now, because this is SN2 mechanism, SN2 mechanism, there's always a reverse of configuration. So the cyanide is going to attach at the back because this group was in front. Configuration very important, okay? Because if you put it on a dash, that is going to be wrong. I mean, on a wedge, it's going to be wrong. And this thing is, sorry, this thing is five membered. Is this okay? Mm-hmm. Where did I get the what? No, it's not. It's not anything. It was just a writing. Mm. Okay, let's look at B now, or part two. So these mechanisms are very easy once you understand what happens. And if you notice different mechanisms, like they have got something in common. What happens? Something in common. If you do a lot, you understand that. So meaning that even if they construct a very new question like they did in those tests, you can actually still answer them because you know the mechanism. Whatever they get to put, you already know, okay, if I've got this reactant, this is a product, and it can't confuse. Okay, let's look at B. Now look at B. The reactant we have is HBr. And I think we already know the mechanism. When you have got HBr and then we have got an alcohol, what happens? Okay, so the first thing that is supposed to happen is the oxygen is, we need to make hydroxide a good living group, but because the way it is, it's a bad living group, right? So what will happen is that this will grab this proton, this bond breaks, and then we form this ring. And this reaction, by now we should have noticed that it happens by SN1 mechanism. So this one will automatically break by itself. And then what you are going to see is going to be this with a positive charge here. Okay. Now the Br which we formed can come and attack here. That is going to be a very minor product. So we can actually form something that is more stable than that. So what can happen is that at this point, because what we have in a ring here is a secondary carbocation. At this point we have a hydrogen, even if we can't see it. So I can move this hydrogen to this end. That is the hydride shift. And when we move the hydrogen there, the positive will come where the hydrogen was. We have formed a tertiary carbocation, and which is more stable than the secondary, which was here. And it is this one which will be now attacked by the Br, which we add. This Br has a negative charge. And then our product, major product, is going to be this. Okay. So because this is happening by SN1, it means that this is going to be a mixture of enantiomer, so plus enantiomer. What we mean by that is that if the Br attacked from the front, then we are going to have this as product. And then this methyl is going to be only wedges. If the Br attacked from the back, then we are going to have a product as this, and then the methyl is going to be in front. So simply write, if you want, just write a line and a line, just lines without showing those dashes and wedges, and then just write plus enantiomer, because for the question itself they had not shown stereochemistry. So just write plus enantiomer. Hope that is okay. It's okay. Okay. And then for part 3, we are using SOCl2. These are mechanisms that we need to be able to know. Okay. The reaction, you can see we are reacting alcohol with SOCl3. The first thing, okay, let me first write my alcohol. Now you need to know the structure for S, and these ones are easy: double bond with oxygen, and then I've got two chlorines like that. So that's the structure, and the mechanism is the same as the one we've just from talking about. This oxygen is going to be able to attack this end, and just like we are doing with the tosylate, this double bond is supposed to break. And what we are going to be able to see is this structure: oxygen here, the hydrogen, we have got a sulfur. Now this is a single bond with oxygen. It has got 3 lone pairs, so meaning it is going to be negatively charged. And then this one has got a chlorine and then another chlorine, right? This oxygen is going to be positively charged because it has got a lot of bonds. Just like we did for the previous one, what is going to come in is that, let me just remove this one on top here. Okay. The next thing that is going to happen is that our double bond is going to come back. When the double bond comes back, what is going to happen is that one chlorine is going to leave. Let me write it on top. Don't forget that this one has got a hydrogen there. This is positive, sulfur, and then I've left out one bond there. I'll write it properly. So I've got a double bond with oxygen. Now I'll not write that double bond here. Let me just write it somewhere else. Okay, I can even write it just here. It's okay. And then I've got only one chlorine because the other chlorine has left. So this bond is not supposed to be like that. Okay, it's supposed to be like this. Are we good up to this end? We're okay? Okay. In this mechanism, we also use pyridine. So what pyridine does is that it will come in and be, you can see they've not written pyridine, but we do use pyridine in this mechanism. It actually comes and it grabs this proton just like we are doing with the tosylates, and this bond is going to break. What to be able to form is something like this. Sulfur double bonded to oxygen, and then your Cl. Okay, that is our product. But remember, there was a chlorine which we had released earlier in the reaction. If you remember, there was that chlorine. So that chlorine will come back. That chlorine that we had broken off, it has a negative charge. We have now converted this into a leaving group. We have converted the OH into a good leaving group. So what happens? Just the same mechanism as the previous one, right? So this will come and attack here, breaking off this bond. And then the product is going to be a chlorine here. Okay. Don't forget, for this one, it will not be a mixture of two enantiomers. Why? Because this reaction is happening by SN2. So meaning that if this one was in front, then the chlorine is going to attach at the back. But the other product that you have formed here is like the same pyridine, right? It has now grabbed a proton. But now we don't show this because they are minor products. Yeah, when you are writing the mechanism, you can just show that the nitrogen is going to be positively charged because every time something which was neutral gains the hydrogen, it becomes positive. But this is not the only product. Remember, we have also released this thing here, which is O with a negative sulfur, like that. So this will be the other product. So this is the mechanism for this reaction. And then we want to write the mechanism for this one. So the first step first, every time you see PBr, now the goodness is all these reactions are similar in mechanism. The aim is we just want to form a what? A good leaving group. So I'm going to use P. Br, I'll write it like this. It has got three of them. Okay, so what is going to happen is that the oxygen, are we able to get me? Okay. The oxygen will be able to attack here. When the oxygen attacks, the BR is going to be able to leave. One BR will be able to leave. We have got oxygen with a hydrogen. It has now attached P, two BRs there. This oxygen is positively charged, right? And then the next thing that is going to happen is your BR is going to come in at this point. So for here, there's no need of even grabbing this hydrogen. That would have been also the case with this previous one. Let me just mention that, okay? It would have been the case of grabbing the hydrogen which was on here. So we'll not even grab that hydrogen because remember the compound that is formed is going to be negatively charged. So the hydrogen that is grabbed is actually going to be able to be the one to stabilize the molecule. So Br now, the Br which was released now comes in. It attacks this carbon in SN2. This releases this molecule. And what you'll be able to see is going to be this. You have your Br. Then the other product that you have formed, you have got H with oxygen with P, Br2. This is a molecule which you leave here. Now let me just state again for this mechanism. In some books, you will see they will not grab this proton. Let me say it, concentrate on it. You are going to see we will not be able to grab this proton. We'll just come direct using our chlorine and just attack at this point and then break off this bond so that the product that you are going to be formed is going to have a hydrogen here instead of losing that hydrogen. And you can see even here we are not we've not even been given pyridine. But again, in other books you see they've not still given pyridine, but that we expected to know that the pyridine is there. So I don't know what people who will be marking will have on their marking sheet, whether they want you to use the pyridine to grab or not. But just an advice, if they don't give it, better you don't use it. If they give it, use it. Okay, now 5. This mechanism is more similar from the one we've actually talked about it already. We are using a tosylate chloride. Can someone tell me the structure for etoslate chloride? Mm-hmm. Uh-huh. Uh-huh. Mm-hmm. Okay. Thank you very much. So mechanism, oxygen will go and attack the sulfur that will break one bond. And then the structure that we end up with is going to be like this. Oxygen here with a hydrogen. We have attached it to sulfur. This one has got a chlorine. Remember, it has got now oxygen with a negative charge here. And then it has got a double bond with the oxygen. And then it has got this group. What is the next thing that is supposed to come back to come in here? Since we are just going through what we already did. What is the next thing? Okay. So this will come back. That is going to release a chlorine. Thank you. So that is going to give us still this compound. Oxygen here, a hydrogen, and then we have got uh, sulfur to now have a double bond with oxygen, another double bond with oxygen. Now it has got this group down. So at this point, oh, this oxygen is positive. Don't forget that. So you can see here we haven't been given pyridine, but then we know that this reaction. So this is where it becomes weak. This reaction is like in association with the pyridine every time you're using tosylate chloride. Okay, so bring in your pyridine because you can't just leave it here. So that was the same case with the previous one. So whatever that you put on the marking key, it will be the one that they are going to use. But then it will still come out as a right mechanism. Okay, so this will be the end product that we are going to have. We don't have any other reactant to come and attack from the back to be able to release this. So this will be the final product. Does this make sense? Is this okay? Okay. Let's hope people are not confused anyway and then they are just quiet. Okay, let's do this one now. So what we have is this structure. The same thing we've talked about over and over now. Yes? Yes, please. Oh, I forgot that. So that is very correct. I've forgotten that. That is very, very correct. I thought there was no living group. So on the previous one, where we ended here, we have an oxygen, a sulfur, double bonded to oxygen, double bonded to oxygen. Okay, don't forget. I forgot. So don't forget if it comes for yourself. So remember there was a chlorine which was removed from the tosylate chloride. So that chlorine is the one which comes in. Very important. Thank you so much, Doc, for that. And this one will come and attack from the back. So the answer that you are going to have is going to be this. So be your final product. Yes, it will have an H, but just know that for this mechanism you always use pyridine. Okay, this one. What do we think is going to be the first thing that is going to happen? Okay, this one is going to go and attack. Thank you very much. This bond breaks off. Don't forget, we have got a BR that has been released because this one will come in at the end to act as a nucleophile. And then we have got P, BR, then another BR. C is positively charged. This bromine which was released will again come in. And then this will break this molecule. So the bromine has come, it will attach on the back. If you write again on a wedge, it becomes wrong because this is SN2. B, consider the following reactions and predict major products for each. Provide a detailed mechanism for reactions 2 and 4. Okay, the only one for 2 and 4. Let me, for that sake, okay, when you are reacting something with chromic acid, this is called oxidation. Actually, all these they've given here are oxidations. These are reactants which we use for oxidation. Now we know by definition that oxidation is gain of oxygen or loss of hydrogen. So if I've got an alcohol, for an alcohol, if I lose this hydrogen of an alcohol, then I've oxidized the molecule. And these molecules, that's what they do. So these molecules, they'll be able to convert alcohols to either aldehydes, ketones, or carboxylic acids. That is what we need to know about them. In other words, they are oxidizing agents. Starting with chromic acid. Now, they don't want a mechanism for chromic acid here. For that sake, let me just show it, right? For that sake. Now, one thing that you need to know about chromic acid is that what kind of alcohol do we have here? Is this primary, secondary, or tertiary? Okay, primary alcohols are going to be converted to carboxylic acid. When you use dichromate and when you use, when you use chromic acid and when you use this guy, these are strong acids. Take note of that. Strong acids. It's not, sorry, not strong acid, but strong oxidizing agents. PCC is also an oxidizing agent, but when you use it, it will not convert to carboxylic acid. Instead, it will end at an aldehyde. That is very important. If you miss that, the first oxidizing agent on reaction 1 and reaction 2 are strong oxidizing agents. So they convert primary alcohols to carboxylic acids. They are going to convert secondary alcohols to ketones, both of them. Even PCC converts secondary alcohol to a ketone. But then PCC, a primary alcohol, it doesn't convert it to a carboxylic acid, it converts it to an aldehyde. These guys, they don't convert tertiary alcohols. There is a question which came in test 2. Give a simple test to differentiate. They mentioned should be a tertiary alcohol. I don't know if it was a secondary alcohol. So that was one of the solutions that we could have been mentioned. Tertiary alcohols do not undergo oxidation, but primary alcohols can undergo oxidation to form dash or secondary alcohols can undergo oxidation to form dash. So that is, this can be used as a test to differentiate primary and secondary. I mean, to differentiate primary secondary alcohols from tertiary alcohols. Tertiary alcohols will not be able to react. Very important here to take note of that. Now, for this sake, let me not write the mechanism here. For chromic acid. Anyway, let me start with something simple. I know it's not here, just for the sake of understanding. Because for primary alcohols is trick, secondary is much easier. Let me start with the secondary alcohol so that you just see how it happens, and then we can talk about the the primary, because the primary is trickier than this other one. Now, chromic acid is Cr, double bond to oxygen, double bond to oxygen. You can see it has got two hydrogens, and each is going to have an oxygen. So the mechanism is going to be the same as the mechanisms we've been talking about generally. But then the first thing, what acts as step one? In step one first, chromic acid, this same structure that I've written here. Let me write it like this. Chromic acid in step one is going to react with water, protonated water to be specific, because we are going to be losing OH, and OH2 is a good leaving group. So this oxygen has got lone pairs. What it does is that it grabs the hydrogen from here, and then this bond breaks. Now when that happens, what are we going to form? We'll simply have a hydrogen attached here, and this is going to be positively charged. So that is one product, and then the other thing that will be released is water. Okay, so this is what we're going to be able to use. And then now your OH oxygen can come and attack here. This will break the bond with the hydrogen there. And the structure we're going to be able to see is this oxygen has attached. Let me write this properly. We have got this. We have got oxygen here with an hydrogen there, and then we have got this oxygen as is now going to have a positive charge because that it has bound to chromate. It is going to have a single bond, and that is going to be OH. This is OH also this side, and then there's also another OH, which is this one here, and then there's a double bond to oxygen. The next thing that happens now, our group, the group that we are going to be able to use, is going to come in. Now this is interesting. It's a very nice mechanism. For the others, remember what we were doing is I hope you can remember, when you are forming an alkene, you grab a hydrogen from a carbon that is bonded to a carbon that is bonded to your leaving group. So if I grab this hydrogen, this bond actually breaks, and then this bond breaks. But that is not what happens for oxidation. So such a hydrogen is called a beta hydrogen. In oxidation, we grab a alpha hydrogen. We grab a hydrogen bonded to a carbon that is having our leaving group. Okay. So we are going to have now our acid to come in, and the acid that we can use even water. And remember, at this point we had the water being produced. We can use water. This water will come and grab this proton. The bond will break and form here, and when that happens, this bond will also break. So look at what you form. You are going to have this. So I formed a double bond here with oxygen, but then you have got a hydrogen. So this guy is still positively charged. Another water molecule now here can come in, grab this hydrogen, break off this bond, and then now you form your ketone. So this is how the ketone is produced from secondary alcohols as a mechanism. It's different a bit from aldehydes, because you have to reoxidize. When you form this, you again oxidize it to go to a carboxylic acid. Sorry for the disconnection. Are we able to see now? Sorry for the disconnection. Are we able to see? Let's just finish up this. We don't need to come back to this story sheet. Are we able to see? Okay, let's. So since I've already described, let me just describe for primary cause as a mechanism here, so that we get to be with it. Okay. So the first step, step one, pardon. Oh, I actually finished. I didn't know that it had cut. So I'll send you. Go through it. We can also use this one so that we complete this. First thing we said that this oxygen will be able to grab this proton. This bond gets to break off, and that will be the product that we are going to have. Cr double bond to, so it will be a single bond, and then we're going to have OH, right? Actually, it's a double bond, not a single bond. And then this is still a double bond. Okay, and then this is OH this side, and then this is OH this side. In the next step, that is step two, now you're going to have your alcohol coming in. Can you allow me to write this group as R, and then I put OH at the end? Or maybe it might confuse someone. Let me just write it anyway. We have got OH here, double bond. I mean two lone pairs. So what this will do, I'm just going to go direct to what is on top there since we've already shown it. So this one, we have got a double bond with oxygen like that, and this is a positive charge. This one is going to go and attack here. That will make the bond to break. Product, we have oxygen with a hydrogen, and then it is bonded to a chromate here, so it will be positive, and then we have got OH, we have got OH, we have another OH, and then a double bond with the oxygen. Hope we are following up to here. We are good. Okay, the next thing that is going to come in is now we can grab an alpha proton. Okay, an alpha proton like from here. We can use another water molecule to do that. If we grab this alpha proton, what happens is that this bond breaks, right? And then when that bond breaks, this also will break. This is what we did also for the previous question. So I've got now a double bond that has formed here. And then this is bonded to an hydrogen. So this will be the end at one step. So if this was a secondary alcohol, we could have just removed that hydrogen and formed our ketone. But then this is a primary alcohol, we're supposed to form a carboxylic acid. So the mechanism is going to happen a bit like again. So don't get confused. Okay. So we're going to have another water molecule coming in to attack at this point. Instead of grabbing that hydrogen, not grab that hydrogen. Instead, another water molecule is going to come in, OH2, and it will come and attack at this point here. When it does attack at that point, the double bond is going to be broken. Don't forget that this was positive. So I've got oxygen with a hydrogen, and then we have attached oxygen which has got two hydrogens like that, and this is also positively charged. So the process will start to repeat again just like for the previous one, but then here before we do that, another water is going to come in and grab one proton. Remember in the previous reaction, the first thing that was happening is that it was the which was attacking. So this is what we're going to have. The bond breaks. This bond breaks. So we have formed now another OH at this point. This OH will act again as a nucleophile to attack the chromium again. So we'll write out that our compound. Remember it had the hydrogen there, the positive charge, then OH, then OH, then double bond with oxygen. So this oxygen will act as a nucleophile, come and attack here. That will break the bond here. And this is what we have at that point. At this point, we have got oxygen with a hydrogen. Then it's bonded to Cr, which is having OH, also having OH, also having OH, and then double bond to oxygen. If you remember, what were we doing at this step? When we had the Cr having being present on our compound, we have forgotten. Remember, for specifically for this mechanism, what we did was where there was the oxygen which had grabbed the bigger group, we had to remove the hydrogen. Do you remember that? We had to remove this, and then a double bond formed here, and then this group was broken. So we have got now a double bond that has formed with oxygen, but remember it has got an hydrogen, meaning it is positively charged. And then the last step, what happens is that this will just come and grab this hydrogen, breaking off this bond. And then what will form, I can write the double bond down, and then I can write the OH here. So this is the formation of the carboxylic acid. Not a tough mechanism, just go through it again, you'll be able to understand. Very easy mechanism. Okay, for they were saying 2 and 4, we write the mechanism. So now we are using PCC. Now you can see they've just said PCC. This means you should be able to know the structure for PCC. Now PCC is like a mixture. Okay. In step 1, the mixture PCC contains just like the chromic acid, but the only difference, you have got a double bond with oxygen, double bond with oxygen. The only difference is that you have got a chlorine instead of having two OHs. Okay, we have got one chlorine. That's the only difference. This one is going to have a hydrogen somewhere here. And then the other thing that is here in PCC is pyridine. So pyridine is a mixture like that. This one is having a lone pair. So what will happen is that this pyridine will be able to grab this hydrogen coming from this other compound. This will break this bond. And then we have formed Cr double bond to oxygen, double bond to oxygen. And then we have a single bond here. This compound has a negative charge, and then we have got a Cl here, and then we have formed our pyridine. I can also write pyridine like this. Okay. In the next reaction, that is going to be step 2. Now we can use our alcohol which was given. So you've seen the only thing that they want us to see is if we know the difference of between for the product. So before even we even continue, what is the product that we're expecting? What? Yes, analdehyde. Okay. So this oxygen is going to be able to attack now the chromate there, double bond with oxygen, and then it has got an oxygen which has got a negative and then a Cl. So this one attacks. Mechanism basically the same for everything. So please, you need to know PCC. So this will be a single bond here, and it's going to be negatively charged. Also, this one here is negatively charged, and then this one is a double bond. We also have a chlorine. As can who can predict what is going to happen next? Okay, so this is going to come down, breaking off this group. So you see CR, we have got now a double bond with oxygen, double bond with oxygen, and then this is a single bond which has got a negative charge. Let me write this single charge bond on top for a reason. So on top there, that's where I'm going to write the one which has got a single hydrogen. So now the double bond, I write it here, single bond, I write it here. So one has a negative charge. Don't forget that this oxygen, remember, it has got a proton. This is positively charged. Now the next thing that is going to happen is this. What you are going to have is this same oxygen which is on here is going to be able to grab this hydrogen, and then this bond will end up breaking, going like this side on the oxygen. So you have this structure. Yes. Okay, so we want to make something that has got a negative here for the sake of this grabbing that you can see here, which is intramolecular grabbing. Is that? Yes. Now we have got mm, it's a bit different from others. But then, depending with some other books, some other sources, you'll see it will also go the same way we went with the others. Okay, just like we went for the others for some other sources. Okay, so this compound that we have formed here now, remember at one point we had released a chlorine, right? We had released the chlorine. So now we have got a hydrogen at this point. So that chlorine which we released is now going to come in and grab this hydrogen. This will form a double bond here, and this will push out this group. And that is the one which will now result into our double bond with oxygen. So this is the formation of uh, the aldehyde. This one, there's a hydrogen at this end, even if we can't see it. There's a hydrogen there. So that is our aldehyde that we have formed. Now for 3, I'll not show any mechanism, but just know that the oxidation, we already mentioned, the oxidation that happens by that reactant is the same as the oxidation using chromic acid. That's called John's reagent. John's reagent. So can we predict what will be the product? Okay, so it is going to be a ketone because this is a secondary alcohol. Now, we when you're using, so this carbon is bonded to two other carbons. Okay. Now the difference, this is very important. The difference, POCO3 is different with everything else because for it, doesn't oxidize, it actually forms alkenes. That is special about it. It forms alkenes, very important. Okay. In step 1, what you have is our alcohol here. Now we are using POCl3, so that is a P double bond with O. Then you have got 3 chlorines. This oxygen again attacks just as usual. That bond breaks. We have got oxygen with a hydrogen, phosphorus, oxygen. Now this is going to have a lone pair, a chlorine, a chlorine, a chlorine. What is going to happen next? Okay, so a double bond reforms, 1 chlorine leaves. And here we're going to have phosphorus, double bond to oxygen, and then you only have 2 chlorines. So don't forget this is supposed to be positive here. I'm just forgetting that. Now in the next step, what is going to happen is that, remember we have pyridine here. Every time you have got pyridine, we know the function of pyridine, right? It's just to grab a proton. So this is our pyridine, 6-membered, with a lone pair. So this pyridine will come and remove this bromine, I mean this hydrogen, and then this will break off this bond. And what we are going to have is going to be this: only an oxygen, phosphorus, double bond to oxygen, chlorine, chlorine. So this guy is a good leaving group. But when you are using POCl3, we will not grab an alpha hydrogen. Instead, we grab a beta hydrogen. Every time you grab a beta hydrogen, your product is an alkene. When you grab an alpha hydrogen, your product is going to be a carbonyl functional group, which can either be an aldehyde or a ketone or even a carboxylic acid. So the next thing that comes in, remember in the first process we had released chlorine. Normally chlorine was supposed to come and attack here to be able to expel this group, or it could have come to grab a hydrogen at this point to still expel this big group, but here instead we'll use it to form a double bond. Now the possible structures is that we can grab this hydrogen, this bond breaks, this compound goes. So one alkene we can form is this. We could have also grabbed the hydrogen, which is here. This bond will still break and then this group will still live. But then this is a minor product because we are grabbing a primary uh, hydrogen. Is this okay? So we are almost done. The other questions which are remaining are just like more for explaining, not really mechanisms. Okay. So these are just mostly for explaining. Consider the formation of the following compound from from C to H5OH in concentrated sulfuric acid. Give SN1 mechanism. This is very direct. And look, what are we forming? We are forming C2H5 or C2H5. So this is the same compound like C2. Like this, we are attaching to an oxygen. Yes. I can't get well. It's breaking. Okay. So this is the compound that we are forming. This one is an ether, and we are forming it from C2H5OH. So we are forming it from this one. Okay, C2H5. We are forming it from an alcohol, and we are using concentrated sulfuric acid. Cis concentrated. So then we want to give SN1 mechanism. Now step 1. The first thing that will happen is that we are going to have one OH. because we're reacting in sulfuric acid, we're going to have sulfuric acid. Let me write it like so. Okay. Oxygen grabs a proton, the bond breaks. This is positively charged. Because this is SN1 mechanism, what is going to happen at this point? Yes, so this will leave. So we're going to have a positive charge being formed at this point. Carbon 1, carbon 2. Okay. And then the same compound that you have formed here will be attacked by another one of its form. So we'll get again the same reactant that we had used earlier. Pardon? Uh, okay, this is an ether synthesis. Esterification we form an ester, but this one is an ether. So these are different. So this other group will come and attack here. And what you see is that, so we are forming a bond with oxygen like this. But remember, this oxygen has got a hydrogen, and then it has got also another group, and this is positive. And then another water molecule can come in, or even this group here can come in. Since this is concentrated acid, meaning that I've got a lot of my, or can even use water anyway. This will come and grab this proton. This bond breaks. And that is how we form this product. This is okay? Okay. Provide a mechanistic explanation to account for the following observations. Solvolysis of 1-bromo 2-methylcyclohexene in methanol gives a mixture of 5 products. This thing came in test 2. Okay, so how is the mechanism? Step 1. Remember, this one is you are reacting this in what? Um, okay, it's a solvolysis of 1-bromo 2-methylcycle in methanol. In methanol, very important. Okay, so step 1, the first thing first, we have got this our compound. It has got a methyl there, and it has got a Br. Now in step 1, this thing will happen by SN1 mechanism. SN1 is what leads to the production of, mostly if you see a lot of things being produced, just know that it is 1. Can either be SN1 or E1. This thing is going to be released. Okay. What you are going to have is this structure with a positive charge here. Now the first product will come actually from this same one which we have here. So let me write the first product here. I'll write that as step 2. Now two things are able to happen. This can either go by E1 or by SN1. So if it goes by SN1, it means that our methanol, because they've said it's in methanol, methanol is just oxygen bonded to an hydrogen bonded to a CH3. This methanol can come in and attack where the positive charge was. When it attacks at this point, what will form is going to be this hydrogen here and then CH3 here. This is positive. Next thing is another water molecule can come in. Okay, water molecule can come in, or another methanol can come in, because this is basically happening in solution. This will grab this proton, this bond breaks. So what product are we forming from these ones which have been listed? We have formed A. So I can tick A. Is that okay? Okay. So now the next product that can be formed from the same reactor, from the same thing that you have produced here, I'll still write the same one. Okay, the previous one, what we did was methanol came in. It came and attached here. When it attached and then we removed the hydrogen using water, it gave us this compound. Is that okay? Okay. So in the next one now, the same compound, but it will not, methanol will not act as a nucleophile to attach at that point. Instead, what it will do, it will act as it works by an elimination reaction. So look at one carbon away from where the positive charge is. That's how elimination reactions happen. So there is this carbon here. There's also this carbon here. So those two hydrogens are there. This OH can come and grab this hydrogen. If it grabs the hydrogen, the bond breaks and forms a double bond here. So the possible product, one possible product. y- Pardon? Uh, can you can you say that again? Mm. Okay, elimination, we are forming an alkene. So we are basically look at the carbon with a positive charge. You look at then when you see the carbon with a positive charge, look at the carbons just adjacent to it on both sides, and then you'll be grabbing a hydrogen from both of those carbons. That will be the elimination. Is that okay? So this would be. Does that make sense? Okay, thank you. So this will be one product which is that is E. But we can also grab this hydrogen which is here. If we grab this hydrogen, this bond is going to break and form a double bond here. Hope you can see it is very small. I've written it a very small one. So double bond will come and form here. That is another possible product. And which one is that? That is C. Is that okay? Is that good? All right. And then to see the other products which are going to form, the other products are going to form after a shift. So there is an hydrogen at this point. What this hydrogen can do is that it can shift to where this bond is. That's a hydride shift. And what we'll see is going to be this structure. So the positive will now be here. So we can use our ethanol again, CH3H. This can come and attack here. And then what we'll be able to see is going to be ethanol attached here. This will be a positive charge. We'll use a water molecule to come and grab this hydrogen. This bond breaks. You can see the alcohol, we have formed an ether. And which ether is that here now, where they are on the same position? This is B. This same structure which is here can also go in E1 mechanism. Look at where the positive charge is. Look at a carbon one step away from where the positive charge is. But if I look at this one or this one, it is all the same. So I'll just use one in this case. So what can happen is that the same alcohol will come in. This is coming to grab this hydrogen. This bond breaks to form a double bond. So that's a double bond that is resulting. Okay. Okay. Just a moment. All right. So we're having this. So there will be a double bond at this point. So which structure is that? I bet we already formed this structure, isn't it? Yeah, we already formed it. But the other one which can happen is, let me first remove this. We already formed this one. We are looking at that carbon with a double bond at every direction to look at other carbons related to it. You can see there's a carbon on top related to it. So we can grab a hydrogen from that carbon on top of it. Okay. So this carbon has got a hydrogen here. Can grab this hydrogen, and then this double bond will end up breaking. And that will give us a double bond at this point, and then we're going to have a structure like so. And that is going to be D. So that is how these products are going to be formed. Is that okay? Does it make sense? Okay, let's get to finish up. We are almost there. Give the products of the reactions of isopropanol with concentrated sulfuric acid under the following conditions. So what we're having is isopropanol. Isopropanol is like this. So please, we need to know nomenclature. Isopropanol. It's like that. And we are reacting with this with sulfuric acid at different temperatures. So we are reacting with sulfuric acid, and it's concentrated at 0 degrees Celsius, at 25 degrees Celsius, which is room temperature, at 130 degrees Celsius, and at 180 degrees Celsius. Now, what we need to know is that when you react an alkene with sulfuric acid at a very high temperature, like 180, you end up with sorry, what I wrote here, I wrote something else. This is not a structure we've been told. It's isopropanol. This is an alcohol. So when you react an alcohol with sulfuric acid at a very high temperature, remember we talked about acid catalyzes the hydration of alkenes. So if you react sulfuric acid with water and an alkene, you form an alcohol. The same way happens. But when you are moving from an alkene to an alcohol, you use more water than the acid. But if you use more acid, meaning it's concentrated, you are going to promote a conversion of the alcohol to the alkene. So this is actually going to form the alkene. Okay, that will form the alkene like that. Now the alkene will not form like this. Pardon me. Okay. What we'll do is that what do we do in this reaction? We are going to use a water molecule. I mean a sulfuric acid molecule. This oxygen will grab you a hydrogen, this bond breaks, so we form water that will act as a good leaving group, it leaves. And then we can grab any one hydrogen away from, because there'll be a positive charge here, any one hydrogen away from the positive charge. So that is how it comes about. There's no mechanism required, so that's why I'm not showing that. So the product we are going to have is going to be this. Now the same sulfuric acid, but if you do it at a bit of lower temperature, you're going to form an ether. So what happens is that this compound that you have here with an oxygen will just react with itself again. So this is the ether that you are going to form. If you lower the temperature even all the more, what will happen is that, remember, from sulfuric acid you are going to have, I've been writing this compound like this. This proton can actually leave. So you're going to have this guy, which is like this. It's going to be negatively charged. So this one is going to act as a nucleophile. And acting as a nucleophile, to go and attack where there is a double bond with oxygen there, releasing the OH. And so what you're going to have is this group. This group will come and attach here, OSO3H. And from that will be the same product also, like if the temperature is very low. Okay, that will be the same product. So that will be those will be the products. Why may sodium metal be used to resolve to re, to remove, last traces of water from benzene, but not ethanol? Look at benzene. Benzene is like this, alternating double bonds. And then ethanol is like this. And then we're talking about what? Sodium metal. Okay, sodium metal. So what happens is this: when you look at benzene and hydroxide, the alcohol, the ethanol has got an hydroxide. So what happens is that ethanol, unlike benzene, will be able to form hydrogen bonds, right, and end up dissolving the sodium instead of it being able to form sodium hydroxide. Okay, so instead of it being able to grab this hydroxide here to form sodium hydroxide and then be able to evaporate the gas, it will form hydrogen bonds with the sodium hydroxide, and so it will end up dissolving the sodium. So what happens? It will not be able to remove water. Instead, it will dissolve the sodium. But if you look at benzene, benzene is doesn't form hydrogen bonds, all right? But benzene doesn't form hydrogen bonds. So what it does is that it is able to be used. Okay. So due to hydroxide group of ethanol, unlike in benzene, water can form hydrogen bonds and end up dissolving instead of forming sodium hydroxide, as in the case of benzene. So in benzene, you can form sodium hydroxide. You are grabbing uh, water from it, and that will be used to remove last traces of water. So if you have any water in this molecule, to react with it, the sodium, forming sodium hydroxide, and that to remove it. Sodium hydroxide, we know this is we can form it as a solid, and you can remove it. But this guy would dissolve the sodium. Give simple tests to distinguish between the following compounds. Yes. So sodium can form an ion, and this ion can be attracted to these things which are negative, the oxygens, like which have got partial negative charges, the oxygens. So this thing can be solvated. In other words, it's going to be surrounded because you have got a polar solvent. So the negative oxygen will be able to surround it like that. So this ends up you dissolving the sodium. So the other water molecules that you add will just be in solution here. You will not be able to Sodium will not be able to react with them to form sodium hydroxide, and sodium hydroxide can form a solid that you can be able to remove. That is unlike in benzene. In benzene, you don't have hydrogen bonds. Like this molecule is basically non-polar, so you can't form hydrogen bonds with sodium. Because of that, a sodium will basically go and form sodium hydroxide with any traces of water in solution. That will form the solid that can be removed at the end. Does that make sense? Is that okay? Okay. Give a simple test to distinguish between the following compounds. Now, if you are giving a simple test to distinguish compounds, you are just using properties that you know about the compound that you've been given. One propano. What is the structure for one propano? Propano, 5 carbons. One, two, three, four, five. And then it's propano. So we have got OH. And then hexene. Hexene is 6 carbons. One hexane, one, two, three, four, five, six. So what's the difference between these two? This one has got an OH, this one doesn't have an OH. Because this guy has got an OH and then this one doesn't have an OH, what proper do we know about these guys? So this one is insoluble. Why? It has got too many hydrogen bonds. Okay. Wow, this one is going to be what? Soluble. So you can use a simple solubility test, and then propanol is going to dissolve in water, and then the hexane can't dissolve. just by looking at the bonds. And then for the next one, N-butanol and T-butanol. N-butanol and T-butanol. Now, when you look at these two structures, N-butanol can form butanoic acid. How is the structure? One, two, three, four, five. One, two, three, four, five. Five carbons, and then it has got an alkyl functional group. That's N-butanol. T-butanol is like tet-butanol, something like this. It makes like a T, okay? And then you have got five carbons, one, two, three, four, five. Then it has got the OH. One, two, three, four. This is just four. It's supposed to have the fifth carbon here. Okay, five. So this is T-butanol. Now, as you can see, T-butanol is really hindered. N-butanol is a straight molecule. So N-butanol, what kind of alcohol is this? Actually, T-butanol is we are supposed to have the OH here. And then we can have a group there. What kind of alcohol is the first one? It's a primary alcohol. And then this one is a tertiary alcohol. Remember what we said about oxidation of these alcohols. What happens to them? So this one can undergo oxidation to form a carboxylic acid or an aldehyde, depending with the reagent you are using. This one can't undergo any oxidation at all. So that is a simple test that you can use. Okay, oxidation. You can name the reagent that you want to use yourself, whether PCC, chromic acid. You can name the reagent. And then the next one, 1 butanol and 2 butene 1O. So 1 butanol, it's like this. One, two, three, four carbons, and then you have got the OH at the end. 2 butane 1N. So this is like this. It's a butene. At position number 1, I've got a double bond. Position number 2, I've got the alcohol functional group. So it's like that. So what, anything that you can perform that, in other words, what do you know about reactions for the alcohol with an alkene? So 2-but-1N, because it has got a double bond, it can decaralize liquid bromine. That's what we know about it, double bonds. This one can't decaralize liquid bromide. So if you react this with liquid bromide, the 2 butene 1O can decaralize the solution because that's got a double bond. And then the last one, 1 hexano and 1 bromohexane. Hexano, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is hexano, it has got OH at the end. Bromohexane, 1, 2, 3, 4, 5. Yes. So that you, I get you. So you are not naming anything. You are just giving a simple test. In other words, what should you do? How do you differentiate this? What can you do to differentiate that? This is this. This is this. That is all. You are not naming reagents and other things. You're just giving a simple test to differentiate. Is that okay? Okay. So now if you look at the other one that we have got an alcohol with Br. So if you look at the alcohol, when you react it with sodium hydride, okay, sodium iodide, let's say. In sodium iodide, what happens that this one, you are basically going to have iodine like that. The iodine here is going to be able to form a solution. Okay, it will act as a nucleophile. It will be able to attack by SN2, remove the hydroxide. This hydroxide can come and react with the sodium. So that is a reaction that can happen by SN2. But then if you look at it reacting with the 1 bromohexane, bromine is a stronger nucleophile than the iodine. So the iodine will not be able to displace the bromine. So that reaction is not able to happen. So that is one thing that you're able to say here. Okay. So that is a simple test, just a very simple test. Let me first talk about this last one here, so that, and then we do the previous one since it's a bit of a mechanism. Explain the following. Propano boils at higher boiling point than the corresponding hydrocarbons. Propano is like this: three carbons, one, two, okay, with OH at the end. With the corresponding hydrocarbons. The corresponding hydrocarbons include propane, propene, propene. These are the corresponding hydrocarbons. Now this one is going to have a higher boiling point because of hydrogen bonds. It has got a OH that can form hydrogen bonds with the other compounds in solution, and that make it hard for you to be able to break those hydrogen bonds. Because it's hard for you to be able to break those hydrogen bonds, it is going to have a higher energy it will take for you to break them, and that raises the boiling point in comparison to these others. So that is it. And then explain why propano, unlike propane or butane, is soluble in water. Let's look at that. Propano is like this, OH. And then you're talking about propane. Propane is like this. And then butane is like that. Now you can see propano is having OH. That OH can form hydrogen bonds with water, making it soluble. These other guys are non-polar, so they can't form hydrogen bonds with water, making them insoluble. And then the next one, any hexano is not soluble in water. Any hexano. When you hear of any, just a straight chain, six carbons, one, two, three, four, five, six, and then it has got OH. Now this guy is not soluble. It is insoluble in water. Even if it has got OH, which is soluble, it has got too many. It has got a longer part that is insoluble. So this longer part will make the interactions with water repulsive, even if it has got a small part which is soluble. That is why it is insoluble in water. Okay, dimethyl ether. Dimethyl ether is like this. And ethyl alcohol, like this is like this, and ethyl with the OH have the same molecular weight, like they also have the same formula. Yet the ethyl ether has a lower boiling point. This one lower than this other one here, which is higher. The reason has to do with the formation of hydrogen bonds. This one can't form hydrogen bonds. This one can form hydrogen bonds. You don't have any proton here which can form hydrogen bonds. But here you have got a hydrogen that can form hydrogen bonds. So that is why, because the ether has no capacity of forming hydrogen bonds, it has got fewer attractions in solution, and so it can easily evaporate it like that than the alcohol. Okay. So that is it. Now let's answer the last question here. Discuss briefly the Lucas uh, test. Now, when you're talking about the Lucas test, is there a question that I've left out anywhere here? Okay. When you're talking about the Lucas test is a test that is going to be used to differentiate different alcohols, right? That is basically it. You are going to use it to differentiate different alcohols. So you're using primary alcohols and then secondary alcohols and then also tertiary alcohols. Now in the Lucas reagent, what you basically do is you are reacting your alcohol with the with hydrochloric acid in the in the presence of zinc chloride. This is the reagent, Lucas reagent. So what happens is that for primary alcohols are going to react with Lucas reagent at room temperature. Okay, and then they are going to be able to form a cloud PPT after you heat. So on heating and then you use the reagent, you are going to form a cloudy precipitate. When you are talking about secondary alcohols, Secondary alcohols are going to be able to react with the Lucas reagent quickly. Okay, these ones are quick. Tertiary alcohols will react with the Lucas reagent immediately. So in other words, primary alcohols are very hard to react with Lucas reagent. Okay, very hard. That's why we're even heating. For the others, at room temperature, they'll just be able to react. So if you see that your reaction happened immediately, you see a color change, then you know you have got an alcohol. But if it takes a bit of time, then you know that it has got a tertiary alcohol. If it takes a bit of time, secondary. If it doesn't react at all, it only reacts after you heat, you know that that is a primary alcohol. So that is the Lucas test. Okay, the last question: mechanistically account for the formation of the following products actually. So here we have got acid catalyzed hydration of alcohols. What do you form in this mechanism? We've been talking about this already. So first thing first, you have got your acid. The double bond is going to grab the proton. This thing gets to break. But then what you are going to have is going to be the hydrogen always attached to the carbon that is having a lot of hydrogen. It follows the Markov-Nikov's rule. So this will be a positive charge. This thing, there can be a methyl shift. This methyl can also shift to this end. What you are going to have is this. So the positive charge will come here. So this reagent, this one here, can react with water. Water can come and attack here. What you'll be able to see is something like this. Water is attached here. This will be positively charged. That will be the same way with this one. Water will come in. It attaches here. You are going to have OH with a positive charge. In the next step, you are going to use another water molecule. You will grab this proton. You also grab this proton, ending up with your two alcohols that you have here. So that marks the end of this tutorial sheet, and that makes the end of the class.